Thank you for getting this set up. This is perfect. Okay, so we went through last time and we talked about just a refresh on our between groups and stuff, right? Once you finished up interpreting what these mean, right, and sort of getting our overall between groups ANOVA stuff put together, right? Any questions about our between groups ANOVA analyses? So kind of come back to people kind of remember what was going on with that. Okay, cool. What we want to go through now is refresh you on our repeated measures stuff. Good, yeah. Okay. I'll camp out over here today then, I guess. You're excited about that. You know, it's here. All right. So with our repeated measures, remember that our repeated measures designs are going to be looking at evaluating differences in some repeated assessment across in one or more variables across two or more occasions, right? We've got an asterisk here. What's the asterisk there for this idea of repeated measures being restricted to the assessment of repeated measures, repeated assessments across groups? Paired samples. Okay, so paired samples, right? But that would be matched. Yeah. There we go. Matched stuff. Now, technically, from a classic design point, right? If I go through and I have one group of folks and I match them on all these other things, and then go through and say, I will technically can treat them as a repeated assessment. You don't see too much of that anymore, but it's something that can do. So always keep those matched paired designs, or those matched designs in your mind. Now, in terms of benefits of our repeated measures assessments, this is really nice because a lot of things we look at in psychology kind of follow this, the ability to follow some individual repeatedly across time, sort of maybe going through and changing influences can start to be a really powerful thing, right? So, for example, if you're looking at impact of stimulant medication, right? So I'm going to have someone test someone with their medication, off their medication, and then with their medication and on off, so an AB design, right? We're going through and trying to manage or track patterns of how this person is responding across repeated assessments. We could do this in a between subjects design. We could have like, okay, here are people on their meds and here are people off. There's a lot of fuzz in there, right? There's a lot of individual difference. So again, things like maybe if psych and law folks, we're going to go through and we're going to give this jury this instruction with this case under these instructions, and then we change the instruction, give them different instructions. How does that go through and impact things, right? So a lot of the stuff that we're interested in psychology kind of lends themselves nice to these repeated measures designs. These are also a much more efficient use of your resources, right? If I can get one group of people together and just test them multiple times, that's a lot more cost effective than getting one big group of people, testing them under this condition, and then getting a different big group of people, testing them under a different condition. The extent to which we can go through and use the same people repeatedly cuts down on the cost for us. And then what we can also do, if we're measuring the same people over multiple occasions, what it helps us do is it helps us control for individual differences, random error, things along those lines, okay? If I get 2 scores from Abby on 2 different occasions, those scores are going to be less variable than 2 individuals measured separately, right? So I can go through and I can have Abby be in one condition and Johnny be in another condition, and then compare their scores and see whether or not who's scoring higher than the other. What's the limitation of that? Or what starts to complicate that comparison? Is Abby the same person as Johnny? Do they approach things the same way? Do they have the same experiences? There's all sorts of person level differences. We're comparing scores on 2 different people and hoping our manipulation changes one sort of set of people systematically relative to the other one, but there's a whole lot of extra stuff in there, right? But if I go through and I take Abby and I measure her on the first condition and then measure her again on the second condition, my assumption is that it's the same Abby going into all of these things. So the differences that I'm seeing across these conditions, my hypothesis is that's purely because of whatever the difference in the condition is, not because of random person level differences that are going on with things. Okay. So what happens is it makes these very, very efficient and very, very powerful types of designs. Now, the limitations of our repeated measures assessments, if there are carryover effects, right? If I go through and I test you, test your ability to solve this problem, and then you know what the answer to the problem is, I can't test you again on that because you already know there's carryover effects, right? Or if I want you to be walking into some experimental manipulation where you're just kind of neutral, and in the first one I really piss you off and make you real mad, now all of a sudden you're going into that second one and you're in a different state than you would have been before, right? And so we can have some limitations there. With our repeated measures designs, these are more complex analyses, so we have more assumptions. And there's increased conceptual and analytic complexity with these. There's just a lot of different things going on that you have to keep track of, right? So no free lunch, but the reason we're going to spend quite a bit of time sort of working through this is these are incredibly powerful designs. These are going to be the bread and butter of dissertations and theses and lab-based projects and things like that. And they're really cool, kind of fun designs once you get your head wrapped around them. So if we look at our most simple version of our repeated measures design, it's just going to be our paired sample t-test, right? So here we're looking at examining scores, change in scores within individuals across measurements. Okay. So again, remember that for our for our paired sample t-test, the mean of the difference scores is our primary unit of analysis. Okay. What we're doing is we've got data collected at time 1, data collected at time 2, but that's all just a means to an end to get that column of difference scores. All we're looking for is that difference. Okay. So our null hypothesis here is going to be that the mean of the difference score in the population is going to be equal to 0, right? If I measure people on across 2 different occasions and I subtract those 2 scores, there's going to be no difference. The mean is going to be 0. Some people are going to be a little higher, some people are going to be a little bit lower, but on average, population mean is 0. Okay. Alternative hypothesis is that the mean score in the population is some non-zero value. In a non-directional test, we're not saying it's bigger or smaller necessarily. Hopefully you have an idea of which way it's going, but the test is just saying, I don't know, it's some value that's not equal to 0. Okay. So just diagramming this out, we're saying in the universe, right, there is some hypothetical score for if we were to take everybody in the universe and sort of measure them once, measure them twice, subtract those 2, that score would be 0. We obviously can't do that. So what we're going to do is we're going to draw hopefully a representative sample, measure them on a couple of different occasions and see if the difference that we're seeing is greater than what we would expect due to just random chance. Questions? Okay. Yeah, so our question here is, do the difference scores across multiple assessments deviate sufficiently from 0 to conclude some non-zero difference in the population? Okay, this is just getting back to all the stuff we talked about, understanding what's going on in our conceptual models. So if we go through, take a look at our data here. This is just a review on our paired sample t-test. Going through and calculating this, we're just taking the mean of the difference minus the expected value of the mean under our null hypothesis, which is going to be equal to 0, right? So it ends up just being the mean of the difference over the standard error of the mean of the difference. Standard error of the mean of the difference is just the standard deviation of the difference scores over the square root of n. Okay. So here we've got a small set where we've got participants A, B, C, and D, scores on time 1, scores on time 2, and here's our difference scores for these individuals. Okay. And if this column of difference scores, we get the mean of the difference, we get the standard deviation of the difference, we can then go through and calculate our paired sample test. Okay. And so again, we're looking at the probability of obtaining a set of difference scores with a mean of 3.5, assuming that the null hypothesis is true. Assuming that there's no difference out there in the population, what's the probability of me obtaining a scores in a sample of this size having these characteristics over here? Okay. And just kind of a quick throwback, what essentially is our paired sample t-test in terms of other t-tests that we've talked about? People remember?
The ones
Yeah, yeah. We're just running a one sample t-test on a set of different scores. That's all we're doing, right? And this is the thing, like people will get, repeated measures will get in people's heads and be like, oh, this is something crazy and fancy and stuff, which there are crazy and fancy stuff going on here. But our paired sample test is just a one sample t-test on a vector of different scores. That's all it is. If you were to go through and take those different scores and just run a one sample t-test on this, and set your expected your null value equal to 0, you're going to get the exact same value here. Okay. Sometimes people will go through, and there is methodologically a problem with different scores or not. If you go through and you take one score and you subtract a different score, a second score, that difference, the reliability of that different score is not going to be as good as the reliability of any one of those things individually. But this is essentially what you're doing for all paired sample tests. It's just a one sample t-test on a vector of different scores. Okay. So again, just wanting you to know and remember that sort of what we're looking at, sort of the main sort of the stuff that we're working with here are these different scores. Okay. People sort of feeling back in the saddle with repeated measures with paired sample t-tests. Okay.
What was the last thing you said? Subtracting one score isn't good for the reliability?
Yeah, so what will happen sometimes, Danielle, is if I'm running a study and I'm like, oh, so what I did is I went through and I created a different score to like look at some outcome. Sometimes people get kind of worked up because the reliability of different scores is not great. Like it has that actually has poor psychometric value. So I've got not so much different than our interaction terms, right? We talked about in our moderation models. If I have variable x1 has good reliability, variable x2, I multiply those things. The reliability is the product of those two, so it's going to be quite a bit worse. Same thing happens with different scores. If I'm measuring this thing with some variability and this thing with some variability of my different score is just doubled up because now I've got imprecision in both of these to go through and account for. And so you will run into literatures where people get sort of really cranky about different scores. There's a good reason for that sometimes, but that's essentially what we're doing in our very standard paired sample t-test. So just knowing pros and cons and stuff. All right. So what happens if we go through and take that paired sample t-test and extend this out to look at not just 2 different occasions, but multiple occasions, right? When we go through and we take a look at our clean subjects designs, okay? Let's say we've got our rows are participants, and these are different conditions, okay? So we got treatment 1, treatment 2, treatment 3, okay? What we assume is that these individual cells are independent and uncorrelated with one another, right? And if, let's say that I've got Mandy, Daniela, and Kate here, I've got Mesa, Olivia, and Lindsay here, and Allison, Haley, and Gabe here, and I go through and I measure sort of what's going on, I'm assuming that all those scores are going to be uncorrelated with one another because they're all independent, they're all different than everybody, okay? And because we've got different people completing different treatments, correlations across these cells are expected to have a value of 0, okay? Now, instead of, let's say, we go through and treat these as all individual people all hanging out in the same design, let's say we have the same people complete conditions, complete whatever we're doing across all 3 conditions, right? So now we just have Kate, Jalen, and Abby here as our people, and now we just have them go through and first complete treatment 1, then complete treatment 2, then complete treatment 3. In this situation, we would not expect all these to be uncorrelated. We would expect actually some hopefully reasonable correlation across these cells because the same people are going through and completing these things, right? So we would expect in this scenario where we have the same people going through and completing this, we would assume some dependency, we would assume correlation across these repeated assessments, okay? Now, typically this is problematic. With our between groups designs, if we violate that assumption of independence, everything's gone sideways and we've got bias tests. But with our repeated measures designs, We go through and allow this because we're explicitly modeling this. We know where these correlations are coming from. We know how to deal with it. We know how to account for it. And if we can go through and do that, that's what makes these very, very powerful designs, because we can take that correlation due to individual differences and we can pull it out. And what's left is a more pure form of whatever effect it is that we're trying to find. So here, if we go through and take a look, just as a demonstration, with our table here. If I go through and we think about approaching this from a between groups design, right? What we would see here is high levels of within group variability and not much difference across groups. Okay. Gabe, if we're looking at this as just a straight up ANOVA model, where's my within group differences? Where am I seeing what my within group differences in this?
Within group?
Yeah.
Treatments.
Yeah, right here, right? So if I look within treatment A, a lot of variability, right? Different people scoring very differently. Here, different people scoring very differently, different people scoring very differently. Haley, if I look at my between groups, where are my between groups occurring?
Between the bottom.
Yeah.
Yeah.
Down here, right? Here we got 16, 19, 21. There's some differences, but they're not that much. And if we look at the between group differences relative to the within group differences, within group variability is much larger than the between group variability. And so what's our overall F test for this going to be if we were running this as as an ANOVA model? F's going to be really small, right? Because I've got a really small number on top, my effect or my sum of scores between, or my sum of scores within, which is going to be really big, and I'm not going to have much of an effect. I'm seeing much greater differences within people in my condition as opposed to across, right? So I'm pretty bummed if this is the situation, right? But if I actually look at what's going on in data, it looks like the variability between individuals doesn't have anything to do with the variability of effect, okay? If I go through and actually look at what's happening, what I'm seeing is that across treatments A, B, and C, we're seeing pretty systematic, similar increases as we move forward with stuff, right? So if I go through and I will go through and let's say, if I look at this from a repeated measures design, let's say I have 4 participants here. Participant 1 scored really low, a lot lower on whatever I'm measuring, a lot lower than everybody else, but we've got increases from 2 to 4 to 7, right? If I look at person 4, this person is way higher overall, right? This person has a different approach or different characteristics that's making them score very much higher. But if I go from A to B to C, we're still seeing that same sort of linear increase moving across there. And same thing with all of this, right? And so what we're seeing here with our repeated measures assessment, even though people are very different in the levels that they're scoring at, they're all behaving to these sequence of treatments all in a very similar fashion, okay? And so what we can do with our repeat measures ANOVA is we're going to reduce that error variability by partialing out the individual differences. All the stuff that makes these participant 1 different than 2, different than 3, different than 4, just due to random, like just different people, we're going to pull that out. And then with what we're left with is just looking at the extent to which the scores are changing across repeated assessments once we pull out all that noise. Okay. What we do is we are again pulling out this overall error. We're reducing our error term because we're pulling out individual differences, pulling out that noise. If I have less noise, I'm better able to detect my signal. And what I'm able to do is end up with a much more powerful design here. Okay. Do people see where this is sort of conceptually how this is working? Okay. So if we think about how this happens, how we go through and tease this stuff apart, this starts to become important. Like sometimes back, oh boy, partitioning variance, snooze fest. Problem is when we get into these more complex designs, where these different components of variance land starts to become important for calculating effect sizes and different contrasts and things along these lines, right? So with our one-way repeated measures ANOVA, our question is, do scores vary across repeated assessment of some variable X, right? If I measure this thing 1, 2, 3, 4 times, do I see differences overall across these repeated assessments? Now, just like when we talked about going from T-test to ANOVAs, if I have, let's say, here 3 different assessments, is there an easy way for me to go through and tease out a difference score out of these 3 assessments? Nope, I can do A, B, A, C, B, C, but that's 3 different measures that are hard to go through and think about, right? So what we're gonna do with this is the same thing we did with our ANOVA models. We're gonna think about differences in terms of variability, right? If I have no difference between a set of scores, my variability is gonna be next to 0. It's gonna be very small, right? If I've got a lot of differences, big differences as people move through this, I'm gonna have more variability indicating differences across my sets, okay? So my null hypothesis here is gonna be that the mean of repeated measure 1 is equal to the mean of repeated measure 2, so on and so forth, however many repeated measures that we have here. So when we're going through and partialing out our sums of squares with our repeated measures in. Now remember someone tell me what a sum of squares is conceptually? You remember?
Some of the squared differences from the mean.
Okay, perfect. Exactly right. Sum of squared deviations from the mean. And Allison, what is this conceptually that we're talking about then?
The sum, is that what?
Yeah, conceptually, like high level concept. Well, what are we?
Sounds
It's
like
like a
variation.
Variation, yeah. It's just,
Sorry.
no, you're exactly, it's just a raw measure of variation, right? Just like anything else, like variation, we can get variation as indicated by range, as indicated by standard deviation, as variance. In ANOVA talk, what is mean squared? What does mean squared represent? Just variance, right? Like literal, like variance, not we're talking about variability as sort of our all encompassing thing that accounts for these different things. Mean squared is just a variance estimate. Like you would calculate sort of at any time, right?
So
So-
sum of squares variation.
Sum of squares is variation,
Like
right? Mean squared, that's actually your actual variance. You could take, if you take your mean squared and take the standard or the square root of that, you get a standard deviation estimate, right? So when we're pulling this out, what we're gonna do in partitioning our sum of squares for our one-way repeated measures ANOVA. So we've got our sum of squares total. This is just gonna be the sum of the squared deviations of each individual score from the grand mean, right? This is all the variability. This is the total piece of the pie we have to work with here, okay? What we're gonna do of that total variability in the set, we're gonna separate things off into difference between subjects variability and within subjects variability, okay? We're completely separating these out, okay? Our sum of squares between, this is gonna be calculated as the mean of my participant or my participant mean minus the grand mean squared, okay? So if I look up here in my little small table here, this is only 4 individuals here. What I would do is I would take 4.33 and subtract 18.76, square that, add that to 11.67 minus 18.76, square that, this from this, square that, this from this, square that, and then multiply this by K is going to be equal to the number of repeated assessments that you've got. Okay. So again, we can see conceptually our between subjects is just looking at overall means or the overall average of people's scores and pulling that, subtracting that from the grand mean. And we're taking that variability and pulling that off. That's just all the individual difference stuff, has nothing to do with how people are scoring across these assessments. It's just their overall mean score. Okay. Our sum of scores within then is just going to be the sum of scores total minus the sum of scores between. So just by subtraction, we get that, we just pull that off to the side. But now what we're going to do with our repeated measures assessments is we can go down through and we can separate that sum of squares to stuff that's specifically due to our repeated assessment versus the stuff that's due to just error here, right? So my sum of squares for my repeated measure is going to be the mean of my repeated measure, the sum of the square deviations of my repeated measure minus the grand mean. So here, if I look at what's the average score for everybody in treatment A, right? We take that, subtract from our grand mean, square that, the mean for condition B minus this, square that, this minus this, square that, multiply that. This is assuming a balanced design by the number of people in each cell. Well, I guess for a one-way repeated measures ANOVA, you have to have equal cells because you have different people in different ones, right? So correct, this is just what your cell size or the number of people you have in each cell, which is equal to the number of people in your sample, essentially. Okay. But what we're doing is here you can see what we're doing is we're looking at variability of these repeated assessments across everybody else. Okay. And then what we've got, our sum of squares error. We take our sum of squares total minus our sum of squares between minus our sum of squares repeated measures. We're just left with whatever random error is left over in these data. Okay. People seeing conceptually where this is coming through and where this is breaking out. So when we're going through and thinking about this, always think about your repeated analysis as first taking your total and separating off into sum of squares between and sum of squares within. Okay, that's the first thing we're always going to do. And the primary reason for separating out the between is what we're doing is we're absorbing those correlations. We're absorbing all that individual difference that's going on within that repeated measures, pulling that out and tossing that in an error term. That's something that we're just taking this big piece of individual differences out of our error term. So if you think about it between subjects ANOVA or standard ANOVA, here's our error term, anything that we're not accounting for. With our repeated measures, what we're able to do is go through and pull out of that total stuff, what's just individual difference? What's just differences because people are different than other people? Pull that out, and now what we've left over within our error term is something much smaller. And remember that our error term is always going to our denominator of our F statistic. If I'm dividing something by a smaller number, as opposed to a larger number, we get a bigger F test, and we get a more powerful test with this. All right, questions about conceptually what's going on with these analyses, how we're going through and doing stuff.
Yeah,
Yeah,
would you be willing to
absolutely.
walk through each?
Yeah,
Like,
what's that?
do each of those based off of like the example up there a little bit? Like what would the SS total be?
Yeah. So
0.76.
what's that?
What would the SS total be?
The actual score?
Yeah.
Oh, I
You
feel
need more,
well,
you need a variance.
no, I can go through and do that. You can just go through and with the information that you have here, you can calculate it out. What it would be, I don't know. Actually, the answer was yes. They have a marker.
I There's no work.
Well, you got the
They're really
fancy
Oh.
overhead pens
Math
here.
house.
I'll do this. Okay, so let's say just for, we won't go for sum of squares total. Well, for sum of squares total, this is going to be the sum of, it would be 2 minus 18.76 squared plus the summation there. This plus 10 minus 18.76 squared plus 22 minus 18.76 squared.
Gotcha.
For the whole set, right? And that's just your variability for that you would or your sum squares that you get for everything, right? So this is just your total. Your between, right? This is going to be looking at your participant means minus your grand mean, right? So this is 4.33 minus 18.76 squared plus 11.67 minus 18.76 squared plus, and this one is actually shorter, right? Because you only got 4 people in this set, but so it'd be the same thing, right? This is looking at to what extent are people all different. Let's say, Lindsay, if everybody was identical, I just have clones that have gone through and done this. Would I expect these participant means to be very much different if it's all the same people who are replicated with the exact same experiences ever and for always?
They'd be all the same.
They're going to be all about the same, right? Or very little sort of minor differences due to just error, right? But different people are different people, right? They come through, they read things different, interpret things different, they have differences of motivation. all those differences that go through and just, which is a lot that just goes into how people are responding differently. That's what's going on, and that's what we're pulling out of this, okay? So then our sum of squares for our repeated measures, yeah, is just gonna be 16 minus 18.76 squared plus 19 minus 18.76 squared plus 21 minus 18.76 squared. Okay. So again, what we're just doing is we're going to go through and this is what's really cool. If you sit there and look at that equation sort of carefully, you're like, okay, I see what's being separated out here and what's going where. And so I think as you start to, if you want to sort of continue on in research and analysis and some of that's, I mean, knowing kind of conceptually where this stuff is coming, because this stuff's going to come up again and again and again and again. You'll read a methods article and it's talking about, well, what we're doing is we're pulling out some squares between. And you're like, okay, I remember what that is. Conceptually, it helps knowing what's going on, so you can do things like sort of run tests and be like, okay, if this is working the way I think it should be, this is what I should get if I do this. Right? Does that help? So I kind of see where that's coming from, folks.
What is K again?
What's that?
What is K again?
What is
K? K.
Okay.
Number of
Yeah.
repeated.
This is the number of repeated assessments.
Oh, so that's
Yeah.
a 3, right?
Yeah.
So would we, at the end of the dot,
Oh, yeah.
dot there, multiply by 3 or
Yeah,
whatever?
you take the whole, whatever that summation is, and then just multiply that by 3.
And then for like the repeated measure would be multiplied by 4, because there are
Yep.
4 subjects.
Yep. Perfect.
Well, that makes sense. Thank you.
Awesome. Any other questions with this? Yeah, Jalen.
Get the grand mean.
The grand mean,
Yeah.
that's just gonna be sort of, if what I got 12 scores here. It's just the mean of those 12 scores.
Oh, okay.
Yeah, just the mean. And so what's a little bit different with this is you've got the same, so normally if you were taking the grand mean of your entire set, you would just take the grand mean of however many people had scored something in your set. Here, you're gonna have more scores than you have people in the set, right? So just thinking about what I've done is I've grabbed a subset of people going through and running this. Now, can I run a one-way repeated measures ANOVA with just 2 assessments?
Only when it makes sense.
What's that?
Only when it makes sense too.
I could, right? But I mean, essentially what I'm.
Do it.
Yep, it would just be a run paired sample. Same thing as, I can run a t-test of independent sample t-test. I can run that in an ANOVA framework. Nothing illegal that says I can't. It'll give me the exact same thing. I'll just get an F test instead of T, but my p-value is not going to be any different. Same thing here. I could run a paired sample t-test in a one-way repeated ANOVA environment if I wanted to. It just kind of makes things more complicated than it needs to be. Yeah. Oh, sorry. I thought that was a subtle hand raise. Okay.
Oh, you know, don't worry.
All right, people comfortable with this? All right, cool. So some assumptions. Things start to get a little bit more complicated when we get in our repeated measures ANOVA designs. Some of it though is going to be similar. We have normality in the distribution of sample means. Someone tell me, Olivia, do you remember under what 2 conditions does the distribution of sample means start to become normal very quickly?
Increase in sample size
Okay, yep.
and isn't it something where the mean gets closer to like the true population mean, or am I making that up?
Okay, that's what's happening with the distribution of sample means. Distribution of sample means should become normal with the mean of the distribution of sample means equal to the population mean. But that starts to become normal and sort of achieve those goals when your cell sizes start to get larger and under what other condition? Yeah.
If the population is normally just.
Yeah. If whatever I'm measuring has a normal distribution of the population, it'll still pop up there pretty quick, right? So when we're thinking about our means-based test, we're back to worrying about, sort of remembering that our assumption is about the distribution of sample means, not the actual scores that we've got. Different than regression, right? So we can have weirdness in our data. Our scores don't have to be normally distributed in order for me to sort of be okay with things, so long as I have reasonable size cells or some assurance that whatever I'm sampling happens to be normal in the actual population, okay? But if I do have weird scores in my observed cells, if I've got different shapes and unequal variance, right? If I've got things that are left skew, right skew, and unequal variance, then I've got problems. If I've got unequal variances and unequal sample sizes, right? Remember here that whatever my sample size is, in the estimation of my overall mean squared error, my cells with larger or more people in it are going to be more representative because they're going to be bigger. My assumption is that it's all the same across everybody. And so I'm just going to take a pooled estimate of everybody that I've got. But if I've got wildly different cell sizes and wildly different variances, that can start to mess with my analyses. If I've got violations of normality in small sample sizes, I've got cells of, and then you don't see this so much, I guess, for experimental folks, like what is like a reasonable sized, what would be a small cell size for you all in research? If you were like looking at a thing and like, oh, like what number would have to show up in terms of individual cells before you'd start to be like, boy, that's maybe small.
That's not 30, I think.
Depends on the test.
Yeah.
But for
I don't
ANOVA,
know, we read a study one time that had like 30 different vignettes. So there was only like 8 people per cell. It wasn't great,
Yeah.
but it happens.
Okay.
I think the general rule of thumb is like 30 per.
yes, percent.
Okay.
That's what.
And this is the thing, if you can get 30 people per cell, you're pretty good. Like that's a nice cell size. But in sort of this study that you're talking about with 8 people per cell, historically that was much more common, right? Like you get like old school stuff out of the 50s and 60s and people just like tossing out 7, 8 people per cell. Now, if you've got 30 different vignettes, boy, maybe what you would do is cut down on the number. I would ask, do you really need 30 vignettes, right? And are there meaningful comparisons between all those 30 of those vignettes that would actually sort of be interpretable that means something? Or what I would do is just get, if they got 30 times 8, 100 or 100 and 30 times 8.
3 times 8.
What's that?
3 times 8.
No, 30 times 8, yeah.
Oh.
What's that? Yeah, 180, no, the 24, yeah, 240 people. 240 people in the set, and just run those people all, maybe not 30 vignettes, but have them do all the vignettes, right? Now all of a sudden we've got, assuming that you don't have problems with carryover stuff, now you've got a much sort of tighter design, right? So with this stuff here, these are all still the same assumptions that we had before in your between subjects ANOVA stuff. Okay. Same thing. We're assuming with our one-way ANOVA, we're assuming a homogeneity of variance across intervals. Now, when we're going through and testing this within our one-way repeated measures ANOVA, you're not going to get a Levine's test for repeated assessments. Okay. What we're going to do is we're going to go through and estimate this with our F max. Okay. So the assumption is the variability for treatment 1 is equal to variability for treatment 2 and variability for treatment 3. Right. So what we're assuming is that across repeated assessments, we're not getting very different variances in whatever we're measuring across time points. Right. Now, our design is pretty robust to simple homogeneity violations, so long as we're not pairing that with wildly unequal samples, which we can't with a one-way design, so that's good. Or different shapes and things like that, we're probably going to be okay. All right. But remember that F max is your ratio of your largest or your smallest variant, or the largest variance to the smallest variance. Okay, so what I would do here is I would look at and calculate my variance for if I've got, let's say, 4 repeated assessments, right? I'd look at the variance at time 1, time 2, time 3, times 4. I find this, the largest divided by the smallest. That's going to be my F max. Okay. Now, if I've got a relatively balanced design, with the one day we design it, it's always going to be balanced because you can't have different people in at different levels of the assessment. F max less than 10 is probably going to be okay. This means you got a lot of latitude in this, right? Like basically you're saying the largest variance across these repeated assessments would have to be 10 times the size of the smallest in order for you to start sort of saying like, oh, well, you got something more. Okay. But when we get into when we're throwing between subjects factors here, now all of a sudden, if we've got unbalanced designs, F max greater than 3 can start to cause some problems. Okay, so again, thinking about this, and so again, inflated type 1 error if the greatest variance is in the smallest cell. Okay, someone tell me this, why does this make sense? Like, so why would I expect greater type 1 error if I have an unbalanced design and I have my largest variance is included in my smallest cell? Yes, yeah.
You're kind of all over the place, like there's just a lot of variability, like room for error. It's
Yeah.
not very precise.
What is it gonna be about my largest variance estimates being in my smallest cell that could contribute to greater type 1 error? Yeah, Kate?
Like in 20 full weeks.
Yeah,
So overall model.
right. So my cell with my greatest variability or my greatest error, right, is gonna get the least amount of weight because it's in the smallest cell. And so presumably those cells with smaller variance, right, are gonna go through and get weighted more heavily. And so the assumption is that they're all the same. And if they're all the same, it doesn't matter what I weight things because they're all the same, but in actual practice, they're never exactly gonna be the same. And so if I have things that are unequal, what I'm gonna do is I'm gonna overweight the cells with the smaller variance, which is gonna contribute to a lower mean squared error, that's what's going in the denominator of my F test. It's gonna make my F test too big, and I would associate that with greater probability of saying I have something when in fact I don't. Okay. So again, when we're going through and doing your screening and things like that, wanting to think about not only if you have violations of homogeneity of variance, think about what are the potential consequences of this, right? Like, is this going to make my test too liberal, or is it going to make my test too conservative? Yeah.
So just for clarity, you're saying that we'll tend to overweight this when the smallest cell has the greatest variance?
Yeah.
Is that what you're
Every time
saying?
I've already marker. So let's say I've got time 1, time 2, time 3. I'm assuming the variance across all these are the same, right? That my model is just saying it's the same. And so let's say time 1, I've got a variance of 5. And I've got time 3, I've got a variance of 50. And here maybe is, I don't know, 15 or something like that, right? Now, if I just go through, let's not pretend this is not you would have to have the same number of people in each. But let's say that let's talk about this as just a one-way ANOVA, it's just between subjects, right? Here, I've got n equals 100, and here I've got n equals 15, right? In this pooled variance estimate, which one of these estimates is going to get the greatest weight? That one, right? And so what's going to happen, this is going to be sort of fairly trivial, right? But if for time 3, if this really actually is the variance, right? The total variance should be much higher than what it's going to be. But instead, my pooled variance is going to be something that's pretty small because I've overweighted this. And my pooled within subjects variance, or my pooled within group variance, is very small. That's what's going into my error term. So my F test, remember, point over within. If my within is too small, then it's going to make my F test too big. I'm going to say that I have effects more often than I should, which is going to increase my type 2 error. right? But Johnny, if I swap that around, that's 10 and now that's 150. Now what am I gonna do?
What do you mean? What do you?
What's that gonna do to my, am I gonna have more type 1 error or my type 2 error with that?
Type 2.
Type 2 error, right? Because now my condition with the greatest variability is gonna be hugely overweighted for my overall ANOVA. And so now everything's gonna be too stringent, right? So just thinking about when we're going through and identifying violations of homogeneity of variance, what the functional consequences of these are and how this goes through and plays in. All right. And people see kind of F max is simple. It's just you go through and look at your variances, you take the biggest one, divided by the smallest one, that's your F max. All right. Now with our repeated measures ANOVA, we've got variance covariance assumptions to worry about. Okay, this isn't necessarily new, it's just something we haven't talked about at this point. Okay. When we're running these analyses, what we're actually doing behind the scenes in the matrix algebra is looking at a variance covariance matrix. Here on the diagonal, we have the variance of each repeated assessment. So this is variance in scores at point A, variance in scores for point B, variance in scores for point C, and then my off diagonal is my covariances. Someone remind me what a covariance is.
The variance between two variables.
Like, yeah, the variance between two variables, yes, which suggests what?
The degree in which two variables vary together.
To which they vary together, right? And if I were to standardize that covariance, what would I get? Say it, I think you know it. Don't be scared. Okay. No, okay. What if we standardize a covariance, what do we get? What is it, Olivia? What's that?
Variance.
No, variance is just variability within this. Within a covariance is we're looking at the degree to which two things vary together. Yeah, someone just said it. Someone was. It's a correlation. Yeah, it's just a correlation. We've just standardized that covariance, right? We've gone through covariance, same thing as variance. I can't look at a covariance and tell you whether or not that is indicating a high degree of relation between two variables or not. But if I go through and standardize it, I get a correlation, and that puts it on a metric of -1 to 1 that I can go through and say, okay, this is what's going on, right? So again, thinking about conceptually what these terms are, like when people start throwing around sums of squares and covariances and variances and stuff like that, it can get a little bit overwhelming. You're like, oh boy, what does that mean? Where's that stuff coming from? We're just talking about variability, and covariance is just an unstandardized correlation, essentially. It's just talking about the extent to which two variables are related to one another. Okay, so here with our repeat measure design, what we're doing is we're going through and taking a look at this, right? But we have some assumptions about what's going on in this matrix in order for our F tests to work appropriately. Okay. One property that you'll hear of is something called compound symmetry. Okay, compound symmetry is where my variances are equal and all my covariances are equal in the population. What that would suggest is I go through and I measure some outcome on, say, 3 different occasions, and then I look at the variance at time 1, time 2, times 3. And then I look at the covariance between times 1 and times 2, times 1 and times 3, times 2 and times 3. Compound symmetry would say that my variances are identical in the population across all of these assessments, and my covariances are all identical. Okay. Basically, you've got a nice sort of tight symmetrical sort of thing where all the elements are looking very similar. Okay. This is what if a matrix were to demonstrate this property, we would say that matrix demonstrates compound symmetry. Now, this is kind of easy to think about, right? And so easier. It's just saying that all these off diagonal numbers are the same and all the diagonal numbers are the same, essentially, right? This is overly restrictive, though. This isn't necessary for our repeated measures ANOVA. Technically, our assumption for our repeated measures ANOVA is something called sphericity, which is a fun word to say. Sphericity exists when we say, yes, variance is the same across all of our repeated assessments. But we would say that our data demonstrates sphericity when the difference scores of each paired repeated measure have equal population variance, right? That's to say, if I take my set and I were to take the difference between time 1 and time 2 and calculate the variance of that difference score. And then I were to take the difference between times 2 and times 3, calculate the variance of that difference score. And then I would take time 1 and times 3, calculate the variance of that difference score. Those variances would all be the same. And if that were the case, I would say that my data or that my data demonstrates sphericity. Okay, this is the formal assumption of our repeated measures ANOVA. And if I violate this assumption of sphericity, what I get, like anytime we violate an assumption, I get an F test or some distribution that doesn't follow the distribution that I think it should, right? And so now all of a sudden I'm calculating a test, an F or a T or something along those lines, and comparing it against an assumed distribution that doesn't fit. And so now all my statistics are off. Okay. So people see the difference between compound symmetry and sphericity in this.
Kind of, so compound symmetry is like the variance in T1, T2, and T3 are all equal, and the covariance.
Yep.
That's
I mean, the variances don't have to be the same number as the covariances. It's just the variances are all the same and the covariances. So this would be like, let's say this is 154, 154, 154, and then 160, 160, 160, right? Because they're different metrics. These are variances and these are covariances. So compound symmetry would say that my variances are all identical and all my covariances are identical. So just separating those two out. Or this is 100, 100, 100, and this is 5, 5, and 5. That's fine. Okay. Because variances are different than covariances. Variances are just variability within the set. Covariances are the extent to which two variables relate to one another. Okay. Okay. So you kind of got to hang on that. Okay. Now sphericity. Where's
time 1 and time 2, time 1 and time 3, time 2 and time 3.
so if I take the different scores for everybody, for each person, right? So I take everybody's score. So I have, like, think about this in a data set. If I have time 1, time 2, times 3 in my SPSS, right? And I go through and I create a column for differences in time 1 versus time 2, and differences in time 1 versus time 3, and differences in time 2 times 3. So I have 3 different columns of difference variables. If I were to look at the variance of each one of those and they were all roughly the same, I would say that my data has met criteria for sphericity. Okay. Which is a little bit different because my variability at time 1 and variability at time 2 could be different. Like I might have more variability at time 1 and time 2, but if I get the different score and the different scores are not more variable than across those other things, then I've met sphericity. So compound symmetry is overly restrictive. So if I have a matrix meeting criteria for compound symmetry, it's going to meet criteria for sphericity, right? But I could have a matrix that meets criteria for sphericity, but not compound symmetry. Okay. Same thing about this way, Kate. When we go through and we're screening for our paired sample t-test, right? We will generally, just because we're curious and we want to know, look at distribution of time 1, distribution of time 2. But do I really care about distribution of time 1 and time 2? No, right? Because what I'm using that is the difference scores. I could have crazy ass skewed data at time 1, crazy ass skewed data at time 2. But if the difference between those two all line up into a nice symmetrical distribution, doesn't matter what those other things are doing, right? Kind of the same thing here. Sphericity is saying, does the variance of my different scores across all possible time points, combinations of time points, are the variances the same? And if that's the case, then I'm good to go. People kind of understand sort of the difference between sort of these and kind of what our formal assumption is in terms of this. Seems like a lot. And I want you to know conceptually what's going on. So when people talk about it, you know what they're talking about. Good news is, or the bad news, depending on how you want to look at it, is anytime we're running a repeated measures assessment, we almost always violate this. This is almost always a violation. So it's one of those things that, because I always violate it, I really don't have to worry about it all that much. I just assume I violated it and take steps and move on to the next corrective steps. Sort of like the same thing when we're talking about our assumptions of multiple regression, right? Do I ever need to worry about whether or not I've met the fixed variable assumption of regression? No, because I already know I violated it, right? Which is why we go through and screen for multivariate normality, right? Same thing here. I want you to know what sphericity assumption is, but just understand that, like, there's no reason that you should assume that you haven't violated this, okay? Now, sphericity is an assumption of our between groups ANOVA, okay? It's there. We also assume this, but because we're assuming independent scores and are achieving independent scores, we're assuming that our covariances are all 0, so we don't ever have to worry about it, right? But with our repeated measures ANOVA, we're assuming our covariances that aren't going to be 0. If our covariances are 0, if we don't have any variability or if we don't have any correlation between my repeated assessments, there's no reason to be running my repeated measures design anyway, because it basically defaults into a between groups design at that point. Okay. So we know that, so this sphericity assumption is something that's always been back there in the background, but with our between groups design, we just assume that it's covered under independence and don't worry about it. Here with our repeated measures assumption, we're modeling that repeated measures, that we're modeling that correlation. So now we have to think about this a little bit more. But when we're going through and we're working through applied research, this sphericity assumption almost never holds, probably never does hold. And this is just a basic function of time and maturation, okay? For these designs, probably what's going to happen is the assessments that are occurring closer in time are going to be more closely related than assessments that are occurring more distally, okay? So if I'm doing developmental research, and I'm measuring, let's say, neuroticism, right? So personality construct, right? And I'm measuring this in young kids all the way through sort of, let's say, adulthood. The correlation in neuroticism between any two adjacent points is probably going to be a lot stronger than anything more distally, right? And so because of that, what I'm going to get is I'm going to get differences in sort of the strength of that correlation across those different elements of that matrix, which is going to be problematic. Even in situations where I've got, even in situations where I'm doing something within a lab-based design, okay, let's say, Danielle, you've got people coming in and you've got some affect manipulation things. You bring people in, and you're showing them one video, rating their affect, and then 5 minutes later, you show them a different video, rate affect this and this. Still, even with that, you're going to have carryover effects. The correlation between affect ratings for time 1 and whatever your last one is probably going to be less strong than any two that are right next to one another. Okay, and so because of this, because the difference in our adjacent scores are going to be less variable than differences in scores that are more that are farther apart, what we've got is our violation of sphericity here. Okay, so the whole, which is unfortunately when you look under the hood, what happens, the whole like assumption of our design that makes the whole thing work is not a realistic thing that's ever going to happen in real life, right? So what we need to do is move on and just go ahead and correct for this preemptively. Okay, so we have different violations, or excuse me, different corrections that we can go through and do. Our Mauchly test. This is a test developed to look for deviations from sphericity. Okay, and what it'll give us a statistic, Mauchly's W, to go through, and you can look at the p-value and look at whether or not you have evidence for violation of sphericity. But it's underpowered if you've got non-normal data. H-screw throws it off. And so even though you'll get this, SPSS will report this, you'll go through and identify, say, oh, I know what this is, and then promptly ignore it. Okay. So what we do, because we've gone through and we're assuming that we've probably violated sphericity to at least some extent, like most of our other corrections, basically what we're doing is some adjustment of our degrees of freedom. We're saying basically what we're still getting is an F. It's just not the F that we think that we're getting. And so we're making some adjustment to my degrees of freedom to get something that's maybe a better approximation. Essentially what we're seeing is a downward adjustment of our degree of freedom depending on the extent of the violation as indicated by this epsilon here. Okay, that's epsilon, right? All right. Good enough? I think it is. Okay. We'll say that's what it is. All right. If we get epsilon equal to 1, that means sphericity assumption has been met. As it increases, our violations of sphericity become increasingly severe, and we'll typically see downward adjustments in our degrees of freedom. What happens to my test if I reduce my degrees of freedom? I'm running a test with, based on my data, I should run this test with 20 degrees of freedom, but I downward correct and I can only run it with 12 degrees of freedom. What does that do to my test or my benchmarks for claiming statistical significance? Olivia? Yeah, it increases my threshold. It makes my critical value larger, which makes it more difficult to go through and achieve my stuff, right? Which again is generally what happens. Like, not violating assumptions is good because as soon as we do violate assumptions, our correction for a test generally, but not always, will make things more stringent, right? And that's what happens here. So we've got a couple of different corrections. Our greenhouse geyser correction, that's also fun to say, provides a downward adjustment based on a greenhouse geyser version of epsilon, right? So greenhouse geyser calculates its own sort of metric of epsilon and then makes an adjustment there. We also have what's known as a Humboldt correction. This also has a different estimate for epsilon for use in cases where your estimated value of epsilon is greater than 0.75, right? So basically what Humboldt is saying, like, you got a little bit of a thing. Okay, we're gonna go through and make a little bit of an adjustment with Humboldt. Humboldt tends to assign less penalty than greenhouse geyser. There's some other corrections there, and so you know what we used to do in old school times is go through and try and look at like, okay, what's the degree of violation of sphericity, and then like try and make sure like, oh, I could use this as my most conservative test, and this is my most liberal, almost like a kind of a post hoc sort of approach. And then you're back, oh well, I'm going to go with Humboldt versus greenhouse geyser, right? Lots of problems with that, right? And again, because if it's the difference between you're like right on the edge, there's probably not a real meaningful difference between, unless we assume that there's something magical happening exactly at 0.05 and one thing is a complete effect and the other is not. These days, it's just greenhouse geyser. Like that's what people have come to accept. This is the thing you go through and use. And so in your output, this is what you're going to go through and take a look at, is that greenhouse geyser correction in terms of assessing for your for evidence for effects within your repeated measures designs. Questions? Okay. Also, yeah, I haven't checked this, but I'll note that the Humboldt correction in SBS is also wrong. So just ignore that. Greenhouse geyser is right. So, all right. So kind of tying this all together. When I'm looking at participants only once, right? I just have my between group designs. Any variability due to my individual is going to be due to an error term. Like all of these differences that we're seeing within our cells, that's just straight up error. I don't know why it's happening. It could be random stuff. It could be systematic stuff. I don't know, but it all gets thrown into that error term, right? But when I have people and I look at them multiple times, what I can do is estimate those individual differences and start to parcel that out of the error term. I can take those and set those aside. And the greater degree of differences across my people, the higher correlation between my treatments, right? If people are sort of lots of variability, lots of different people coming in with lots of different sort of approaches, what I'm going to get is a lot of variability between people due to individual differences. And that's going to contribute to a very strong correlation across my repeated assessments, okay? Higher the correlation between your repeated assessments, greater power of your repeated measures design, okay? This is Gabe, I don't think you said anything. I was just looking at you when I thought about it. But but so if I go through and I were to go through and run a repeated measures design where across repeated assessments, people's scores at time one were completely different and unrelated to time two, completely different, related to time three. Essentially what we've got there is just between subjects design then at that point, it just reduces it down, right? So the whole point of these repeated, measures assessments is to go through and capture that correlation across things. Now, some things that we measure, we're gonna have very strong associations over time. Sometimes we're gonna have sort of more modest things, right? So if I'm looking at, say, state level mood or something along those lines, I'm probably gonna get some connections across these, right? People are probably gonna go across if I'm going week to week to week in state mood. When I happen to catch you on a given day, it's probably some relation. It's not gonna be super strong, right? Versus if I'm doing, again, like psychophys research, some people have done some psychophys stuff, right? If I've got someone strapped up to a skin conductance monitor, there's only so much my skin conductance can go up and down, right? And so what I can start to see is almost collinear correlations between these things, right? And in that case, what I get is incredibly, incredibly sensitive and powerful design where even small deviations will start to come up, right? So just remember, like, as we're going through and doing that, that correlation is representative of individual differences. What we're doing is we're pulling all those out and then just looking at tests of my within subjects effect here, absent all those individual differences. Questions on this? Okay, cool. By my watch, we're right at 3:30, right? All right, let's go through, take a break, come back at 3:35, 3:36, and we'll jump into actual example. Go through and during the break, go through and open up your those two data sets so we can jump in with that.
Hi, Dr. Cassie. Yeah, Cassie defended today.
Open both of them up.
Oh, what are they called?
Oh, they're just the factorial ANOVA.
Is it?
The exercise RM and ANOVA.
Oh, okay.
Ordered ones beliefs.
Oh, I see it. Everyone else.
All right. Daniel, you switched places.
Doesn't work there.
Okay. Throwing me off base with stuff here. All right, that's okay. I'm just gonna roll with it.
I needed.
Okay.
I had to.
All right, folks, before we jump into analysis stuff,
Thank you so much.
quick update on, we're still working on problem set. Is it 5? Okay, so we got one more left. And
It said
so
6 at the top of it though.
right.
I think we shouldn't have a 6 then.
It's a technicality, yeah. But you know me, I'm always like, oh, you got me on this. What do you think it meant?
Gonna put 5 on the next
So going through, so we had some discussion about final and sort of where people's schedules land and things like that. Gone through, resolved that. We'll hold final as it's scheduled on Wednesday. Just so everybody just plans, so we'll just be here at that the scheduled time. I know, so sometimes it cannot be convenient for everybody all the time, but again, trying to sort of navigate stuff like that. So we'll just go through and do it. But this last exam will just cover the logistic regression stuff, the repeated measure stuff, right? So, and just maybe, what is it, like 2 or 3 articles that are assigned? up to this point, so it's just gonna be a much more manageable set of information to go through and take a look at, so we'll do that on Wednesday. Now, we've got two people who are gonna be out of country for this last problem set that's gonna go through and to create some distance issues in terms of putting groups together. So what we're gonna go through and do, we'll have Kate and Allison, they'll work on their stuff in Sweden. We put a couple of umlauts and stuff like that all over their problem sets, I'm sure. For the rest of us, what we'll go through and what I'd like to do is have two of our standard sets of three and then have one group of two, right? So we'll have, or no, wait a minute, two groups of two and then two groups of three.
Plus
Right.
our group of two.
Plus your group of two.
Okay.
So you're out of the mix. Like we've removed your variance from the equation, right? We've parceled you out and are looking at the remaining 10. So with that, it's the last set. It's a big set. We'll let you go through and choose to work with whoever you want to work with on that. What I wanted to is see you all organize yourself into two groups of three, two groups of two. However you want to do that, just let me know. And that's what we'll do for our final set. Okay? Does that sound good? Perfect. All right. So let's jump into example here for, we got a couple of different sets here. And this is, again, one of those wrinkles that we'll see with our repeated measures designs. Aspects of your data and your design start to fundamentally change how we go through and think about and options that we have for going through and analyzing things, okay? We've got two different sets. The first set, what we're doing is we're looking at inpatients who are receiving treatment for depression. So what we're asking here is, does the pattern of depression scores change over the course of a 6 week inpatient treatment? So we've got symptoms at intake, 2 weeks, 4 weeks, and 6 weeks, okay? Thinking about this, and you probably don't need to be a clinical person to sort of think about like what should happen. What should we see in terms of scores, in terms of people receiving inpatient treatments? We're seeing reductions, right? If I fail to reject the null hypothesis, that's a bad thing, right? Because it suggests that there's no variability in scores, that things just kind of hung out on their own, right? But in this case, what we've got is something that has, where my time or my repeated assessment has sort of a natural order to it, right? It would not make sense to look at this at sort of, is there a change from 3 to 2 to 1 to 4, right? There's sort of a natural temporal order to this. And so that changes the way we think about something along these lines. Now here, we also have a different set looking at post-trauma support. And again, this is a set that we've used before, so it should be somewhat familiar. His willingness to maintain friendship with a hypothetical victim of life stress vary based on the nature of events. So here what we're doing is we're having people go through and fill out vignettes related to motor vehicle accidents, combat deployment, infidelity. So partner was not faithful. Here we have a sexual assault, a natural disaster, chronic illness, work relocation, financial collapse. So we've got some of these things that, at least in my field, we would consider traumatic stressors, and some of these are very, very intense stressors, but not of the type that we would sort of classify as trauma. And so there's lots of different hypotheses that we should have here. But with this example, does it matter what order these are in? Is there any natural order to this sequence of vignettes? Nope, there's sure not, right? And actually, when I was running these data, putting these things together, sort of what I really wanted to do is look at differences across these, but not have to collect a separate sample for each one of those, because I would have had a sample of like 600 or some nonsense like that, right? So thinking about like, okay, can I get a group of people and have them just respond to each one of these vignettes? Now, I don't want, work relocation to follow sexual assault every single time, because there's going to be probably some stuff going on there. How do we go through and maybe start to sort of address some of that stuff?
Just randomize the order. That
Yeah,
people are
just
getting.
counterbalance things, right? Now, counterbalancing actually adds variability in there because everybody's getting a different order. And so if you have order effects, that's perpetuated across the whole thing. But if you've got a big sample and can treat this as repeated assessments, you're still far better off than going through and treating this as a between groups design where I've got 8 people for each vignette, right? So, two different sets, and it's gonna very much change the way we think about this and go through and work through in terms of follow-up and how we sort of try and understand what's happening. Okay. Questions? Okay, so let's go through and open up, let's pull up the ordered means set here. Okay. And then also you've got these 2 handouts, the one-way RM ANOVA handouts. We'll be working through those here today too. So for our ordered means, what I thought we'd do first is go through and just take a look at your correlations, right? I go through bivariate and just look at my correlations between intake scores week 2, week 4, and week 6. And then I go through and hit OK. Why might it be interesting to go through and take a look at those correlations? Are we seeing correlations across our symptom measures? Yep, we are. Does anybody notice anything that sort of is going on in this that might kind of relate to some of the assumptions that we talked about previously?
I don't know if this is what you're looking for, but as the weeks progress, we're seeing a higher correlation.
Okay,
Like between weeks 4 and 6, the correlation is higher than, I guess, from 2 to 6.
okay, kind of, yeah, what's kind of going on with that?
We see like higher correlations between like time points that are closer together than further
Yeah.
apart.
So, Kate, yeah, there is something that goes on that looks like as we progress through treatment, so even these adjacent correlations are starting to get stronger, right? And if you do treatment stuff. Yeah. And if you do treatment stuff, like sort of when people are coming in, everybody's kind of in the same spot, but as people go through, some people respond and some people don't. And so you're seeing tighter correlations as things go down. But just looking at this, would we have any assumption that we've met or any belief that we've met an assumption of sphericity here? No, right? Is what we're saying is the relation between intake and 6 weeks is very different than the relation between 4 weeks and 6 weeks, right? And so again, just as Abby was saying, we're seeing that those assessments that are taking place closer in time are more strongly correlated than those that are happening distally. And so again, we can see very clear violations of sphericity in this, even to start out with. Okay. Questions about that? Okay. So what we're going to do here is go through, and we'll go through and we'll get into screening when we get into the mixed factor stuff, because the screening here is pretty much redundant with things that you've already done for the other betweens designs. But here what we're going to do is we're going to go to analyze, and we're going to go to general linear model, and we're going to go to repeated measures. So what's going to happen when you do this is it's going to pop up a first box, right? And this first box is what you just have to do is you have to define your within subject factor, and it's going to ask you to name it. Doesn't matter what you name it. I'm going to name mine time just because that makes sense in terms of what we're measuring on this repeated assessment. And then it's going to ask me how many levels do we have, okay? How many levels, how many repeated assessments do we have in this data set? 4, right? We're going to go through and hit 4. I'm going to add. Now, if I were to have multiple repeated assessments, like if you're going to get crazy with this, you can have multiple repeated assessments. We're just going to work with 1, so we're just sticking with 1. Okay, so we've defined our within subject factor. I'm going to hit define, and then you're just going to go through and drop in your 4 variables that represent your repeated assessments. Okay, so we've got intake 2 week, 4-week and 6-week with this. Okay. Now here, do we have any grouping factors within these analyses? No grouping factors, it's just we're looking at everybody across repeated assessments. Okay, so what we're gonna do here is we're going to go to contrasts. Okay, what this is gonna do is it's gonna give you a time contrast here, that's fine. Just gonna hit continue. Okay, in terms of plots, SPSS plots are terrible, right? Our plots are brilliant and awesome. You will probably do something in between in terms of Excel, just going through and creating stuff there, right? Well, what we can do, just so we can get a quick visual on stuff, is I'm gonna go through and request a plot where I just want time, my repeated variable, my repeated assessment on my horizontal axis, just so I can get a sense for what's going on, so a graphical representation. I'm gonna hit add, and I'm just gonna hit continue here. Okay. And then I'm gonna go down, I'm gonna select options. I'm gonna ask for descriptive statistics, estimates of effect size. I'm gonna request homogeneity tests. It's gonna give me an error and it's not gonna give me one, but we'll just click it so you can see what that looks like. And then that's good. Okay, and continue. All right, I'm gonna hit OK. You go ahead and hit paste on this. All right. So what we've got here. And we'll just run it up here just so it's bigger to see. All right. We're going to start out again, similar to our logistics. You want to not ignore this. You want to make sure that everything's looking good. So you have here your dependent variable, right? Your outcome variable is BDI1, BDI2, BDI3, BDI4. Want to make sure that that's consistent with what you're wanting to see in your data. Okay, that looks pretty good. Here, we're going through and we're seeing our descriptive statistics here. Mean standard deviation at intake, 2-week, 4-week, 6-week. What I can do here is I can go through and calculate my F max. Okay, now do I have the variance here? Is SPSS giving me variance? No. Give me standard deviation. Can I get variance from standard deviation? Yep. Okay. This is the thing. Don't divide standard deviations for your F max because you'll be wrong, right? Again, because we're squaring these, right? So, but if I go through and I take a look and I want to check my F max on this. My lowest degree of variability is at 6 weeks. So I'm going to take 9.55 squared to get my variance. Whoops. Start with my largest. Largest is at time 1, right? So we got 12.688 squared over my smallest 9.551 squared. Someone tell me what they get for F max here. What do we get, Kate? Oh, yeah, I thought you were looking at me because you had it.
No, sorry.
Yeah, I do.
Ish,
Okay.
1.7-ish.
1.7.
1.8.
I got 1.76 here.
Okay.
Okay. So are we concerned about our F max? No, we're looking pretty good. We've got equal cell sizes because it's a one-way design, right? And remember that like with equal cells, we could tolerate up an F max of up to like around 10-ish. Wouldn't be great. That would for sure something to be sort of mentioned, but we have no concerns here. Yeah.
We're missing like people who miss a week or something.
Yeah.
And then we have unequal cell sizes. Is that factor in here or we're?
You have equal cell sizes because those people get kicked out. They don't get included in the time in the assessment. But this is where in that announcement I sent out, like, Stata doesn't have a good package for doing this. What you would do is look at it in a multi-level model. And if you're running it in a multi-level model, then you're using maximum likelihood estimation, which then goes through and accounts for this. So really for these types of data that we've got here, like this depression example, the mixed factor ANOVA isn't the best way to go through and look at this. A multi-level model or a latent growth model is a much better way to go through and take a look at this. But we can still do it in this way and sort of infer some things about what's happening. And another benefit of that is if someone had missed a week, we can still incorporate them. But for our ANOVA, can't, because as soon as anybody with not full information or not complete data gets kicked out, just like we would in a regression or anything else. Other questions? Okay, so we're feeling good about this. Gonna go down through these multivariate tests. You can go through and ignore these, okay? Back in the day, like in like the 60s and 70s, one of the ways people went through and would evaluate these repeated measures designs would be to evaluate these as like a MANOVA type of a thing, where you're treating one of these outcomes as part of a matrix of stuff. This is kind of what's going on here with the multivariate tests. We don't actually look at those or interpret those, so we're going to ignore those, but I want you to know what's happening. Here we've got our test of sphericity. Do we pay attention to this at all? No, we don't care. We're assuming that we've gone through and violated sphericity anyway, but here's the test, and here it's has a low p-value. Here's your greenhouse guys, your epsilon, your Grunfeld, your lower bound, stuff like that. Again, want to know in general kind of what's going on with this, but not something you have to worry about or interpret. We're just going to assume that we violated homogeneity variance regardless and proceed to our greenhouse gas correction. And so now we get down here into our test of our within subjects effects. Okay, so here is our main effect of session or time, so whatever you go through and measure it, and then here's your error. All right, so someone take a look. Do we have evidence for a main effect of time or session in these data? What do you think, Mandy?
Sorry, say that again.
Do we have a main effect of time, or do we have a main effect of our repeated assessment?
Maybe yes, it's our P.
Yeah, we've got pretty good evidence for an effect, right? For our one-way design, this is our test of our primary hypotheses, right? This is testing that the variability, there's no variability across repeated assessments, right? That mean of time 1 is equal to mean of time 2, mean of time 3. And so we're very clearly saying that's a massive F. That's an F of like close to 430. It's very clear that like these data, the null hypothesis is functionally impossible, right? So feeling pretty good about this, right? But one thing I want to go through and start thinking about, wait, we'll put a pin in that for a moment. So let's go down, and so we've got evidence for our within subjects effect here. So we're feeling pretty good about that. This next piece, here's your test of within subjects contrasts. Let's ignore that for right now, okay? Here you have a test of between subjects effects, and we find that we have a p-value here that's infinitely small. It's associated with an F of 1,158, close to 1,159, right? Any guesses as to what this is capturing here? What is the between, yeah, Kate?
The variability between our subjects.
Awesome. Exactly right. Yeah. This is just saying that different people are different, right? Different people in our sample are just different from one another, right? This isn't something that's terribly useful in terms of interpreting, because we assume different people are different. But this is just capturing and saying, is the between subjects, variability, is it different, right? Is it not zero? Is everybody not exactly the same? Very clearly, it's not, right? But when we go through and start taking a look at your variability here, right? When we go through and think about, remember that we've got, anytime we start with our sum of squares total, first thing we're doing is pulling it apart between sum of squares between, sum of squares repeated measure, right? And we're going to go through and separate these two things out, or excuse me, sum of squares within, and this, there's sum of squares repeated measure, our sum of squares there. Okay. In our SPSS output, where are we getting these different components? Got it.
But is it or the error, it's the error in our greenhouse geyser row?
Yep.
And then the between is the session, same row.
Okay. Now, is this, or this is between?
Oh, no, it's not that one.
No,
It's
okay, so you got error,
Error.
what's that one?
let's say repeated measure.
Yeah, this is your repeated measure,
Uh,
okay, and where is your sum of squares between?
That what we were just talking about.
Yeah, that's down here, that's this piece of things here, right? So this is gonna start to become important when you're going through and you're starting to calculate different measures of effect size, knowing where these different variability proportions are coming from and being sectioned out.
Where was
So,
error?
yeah.
Or within,
What's that?
where was within
So within,
is the home coat?
Okay.
And that was the error.
so does SPSS give us our within? No, where do we get our, how do we get our within?
We need the repeated measures in there.
Yeah, we add those two things to get that, right? And then this is getting sectioned out. Do we get total? No, but if we just add all those together, we would end up at the top.
So where's some of the squares for repeated measures? Was that the first
Yeah,
call? Okay.
This is your effect here. All right, so if we go through and we then drop down for this piece of things, here's our graph, okay? What is happening, Mesa, with this graph right here? Just based on this, what are you guessing is the nature of our within subject effect? Mesa? Oh, I'm sorry, I thought, sorry, I didn't know if you were busy writing and didn't hear me. Yeah, what's the nature of the within subject effect here? Just like, what's happening, just based on looking at the graph.
Decreasing.
Looks like we're decreasing over time, right? It looks like as treatment progresses, scores are getting lower, which is essentially what we would expect. Are they getting lower by a little bit? No, they're getting lower by a whole lot, right? And if we go through and take a look at that F test was massive, right? Very clearly, we're seeing changes in scores over time, which is hopefully what we would see with this type of treatment and things along those lines, right? So we're seeing big decreases here. Now, this is where the problem now is does our F test, Johnny, does our omnibus test of our repeated assessment, does that tell us where these differences are occurring? No, it sure doesn't. So we have to go through and do some stuff to figure that out. Does it probably make sense to do all pairwise comparisons in this set? Probably not, because that's probably just a waste of we're just doing stuff to do stuff there, right? So what we need to start thinking about carefully is, okay, how do we go through and test this stuff? So that was easy peasy, right? We go through, we can do the same thing. We don't need to because it's the process will be the exact same. But if we go through and we're to do the same thing for our unordered means this time, right? We would go through, set up things the same way. Now, this is a little bit different, right? Because there's no natural order to these vignettes, right? Because I counterbalanced the administration of these. So it's a little bit different in terms of when we're thinking about sphericity in that, like, I don't expect one of these to be closer than the other, just the way I went through and administered these. But just looking at sort of this table, does it look like I'm probably okay in terms of my sphericity assumption? Probably not, right? We've got some of these vignettes that are very highly correlated. Accidents and disasters are about 0.75 correlated, so those two things are very strongly related to one another. But if I look at willingness, spread, friendship, following infidelity versus a physical assault, that's a much different correlation between that, right? So even though we don't have some sort of natural temporal order to this, it looks like we still, these things are not, the responses to these vignettes are not equally related to one another, right? They vary quite a bit. So we're still probably going to assume that we violated sphericity here, even within this thing where we've gone through and counterbalanced. Okay. So again, if we come down through, we take a look at our descriptive statistics. Here we get an F max of 3.08. Okay, so a little bit bigger if we go through and square 0.770 and 1.351, right? Gives us an F max of 3.08, but again, not worried about that. That's not something that's problematic in terms of differences in variability. Ignore a multivariate test, ignore Malchi's. Look at our test of within subjects effects. Gabe, are we seeing main effect of repeated assessment here? Yeah, right. And again, all this is saying is that we have evidence that individual response to these vignettes is not identical across each one of these. They're just different somewhere in there, right? And that's all that it says, right? We're not looking necessarily at change here. That's something for HLM and latent growth curve analysis. We're just looking at patterns of means. It looks like the patterns of mean responding, so people's willingness to provide benefit across these different scenario vignettes is not the same. They differ. So it looks like vignette matters in terms of the extent to which people are willing to provide ratings of friendship, at least in this hypothetical, right? Here again, or between, it's just saying that people are different from other people, right? So we're pulling out a considerable amount of variability from this, and then here is our here's our pattern of vignettes. Allison, if I look at this, is there a nice, easy story to take out of this? No, I don't know. It's kind of all over the place, right? So I'm going to have to think carefully about what are my a priori assumptions? How do I think this stuff is going to play out? Okay. Anybody else? Is there anything else about this graph that kind of makes people a little bit cagey? Yeah, Lindsay?
The y-axis.
Yeah.
Scale.
Yeah. What's weird about that scale?
It goes from 7.2 to 7.7, so it's kind of.
Yeah. What's the range of my scores here?
Half a point.
What's that? A half a point, right? And these are scores ranging from 0 to 8. What this is a hyper magnification. Like, looks like I've got wild differences here, right? Like big sharp spikes. But this is microscoped in on something that is actually probably very, very slight. Okay. But again, this speaks to the power of these designs. If I've got a 1 to 8 scale with standard deviations of around 1, do I expect something that's a half a point difference to probably make that sort of pop in terms of that big of an effect? Probably not if I'm doing this as group 1, group 2, group 3, group 4, group 5, group 6. If I would run this as a between subjects design, I would not get anything, right? But what I did with this is just capitalize on the power of repeated assessments. Because thinking about like how much are people willing to help hypothetical people, probably a lot of individual difference in terms of this, right? Now we're seeing it's kind of a loaded question. Like you got to be a real jerk to like in a no cost to you situation, say, how willing would you be to be nice to somebody? Like, we're kind of sealing things out, right? You kind of have to be a jerk to be acknowledged, you're that person. In the hypothetical situation that costs nothing, but people respond how they're gonna respond, right? But what we've done here is capitalize on the repeated measures design and the power of this to go through and actually pull things out. It's giving us very clear evidence that there is some difference going on here. And questions about running just this one-way design, at least getting the omnibus stuff out of it.
I do just have like one quick
Yeah.
question. The air within the model there, where is that at again in the tables? Like where,
This is gonna be so, and if we think about this as this table of within subjects effects
Right.
here, that's this piece of things, right? So we're just
Right.
sectioning all this off to the repeated measure stuff and then the air stuff. We're just sectioning this out. Okay, and then the stuff down here below, that's your between. But what we've done is all that variability that goes in between. Normally with our between subjects design, that all just gets lumped in my error, right? My error term here is substantially smaller because all this, we just took that and we said, that's a different type of error that we don't care about. We're gonna set that aside and we're only gonna focus on this piece of things. So now all of a sudden my error term just went and got really, really small, right? So all those individual differences that got pulled out and now we're just working over here in this part of town. Questions? All right. So let's jump back into conceptual land here. All right, so just omnibus interpretations, okay? Running this is, we're getting the omnibus stuff is pretty quick and easy, like it always is. Just a quick write-up in terms of how we might go through and talk about this. Say results of the repeated measures, ANOVA provide decisive evidence. Like this, I'm like decisive. Yes, gotta have like 1,500 or something like that. So evidence against the null hypothesis of equal depression scores across repeated assessments in the hypothetical population of individuals receiving inpatient care. So this is just me like pulling in all the stuff I'm wanting you all to pull in anytime I'm talking about a hypothesis. We're talking about populations and talking about strength of evidence here. I'm going to say that this is decisive. This is P equals 4.12 times 10 to the negative 142nd, right? My base factor is 7.9 times 10 to the 138th, right? I would have to get, so evidence against the null is similar to that we would expect from 471 consecutive heads of a hypothesized fair coin. Like, I mean, this is just like, this is for sure a thing, right? So very, very strong strength of evidence. Inspection of observed means indicates substantial reductions in depression scores in the course of intervention, right? And that's just based on my sort of visual inspection of this, like kind of what's going on. Yeah.
My interpretive standards on my slides are different than yours.
What's that?
My interpretive standards are different than yours.
Okay, yeah, that's I forgot to fix this.
Oh, yeah.
So these are your interpretive standards should be the same ones as we had previously. I think these ones are, I'll go through. Matt, can you send me an email, go through and check that? So yeah, well, the ones that we had from last semester for base factor is like, these ones are the correct ones. I think you should have there.
Those ones are the.
Yeah,
correct
yeah,
ones?
these ones. Not worth more than a bare mention. I think is maybe my favorite anchor for some interpret. Not even not more than a mention, not more than a bare mention. Right? So for our second one, saying within subject effect event identifies data from current studies incompatible with the expectation of equal willingness to maintain friendship for individuals exposed to various forms of external stress. So again, just kind of changing up how I'm talking about this, just to be fun, right? Results suggest that specific events may influence others' willingness to provide and or maintain support following exposure to stressful events. Okay, I don't know exactly how, but it's just, it looks like it's different. There's something in there that's going on. And that's really all there is to just interpreting the omnibus effect for these one-way models. Okay, very similar to any of our other omnibus effects. We're just saying that there's something going on in there somewhere. But all this is saying is that we have strong evidence against the null hypothesis of equal means across repeated assessments. So again, I'll just say this, be very careful with your language here. This starts to get into analysis nerdery, but we're not technically looking at, this is not an assessment of change. This is an assessment of just mean differences. If you want to actually model change, this is where we're talking about latent growth curve analyses, hierarchical linear modeling, where we're looking at some change function. This is just looking at differences. Okay, so if you run into something, people are like, oh, this is actually an actual model of change. That's what they're talking about with this. All right. So if we're thinking about effect sizes, right? We want to attach effect sizes to this. So strength of evidence, massive strength of evidence, but we've also got pretty large sample sizes with these things. So, right, we want to quantify our effect size independent of sample size here. Remember that our eta squared, right, gives us a proportion of total variance attributable to an effect. Okay. This is just our sum of squares effect over our sum of squares total. Like, what do we see for our repeated measures effect? What's the total variability? We go through, divide those, gives me my eta squared. What's eta squared similar to? Someone said it.
Semi-partial.
Okay, are we
Someone-
partially anything out of here? No. So what is this similar to? R squared. Yep, nice work. This is like our model R squared. Did you say R squared? Someone
I
like,
did earlier, but.
I like small whisperings of things, right?
I
But
wasn't
yeah,
confident.
that's all right. Be confidently unconfident, right? I just, but to go through, if you shout out something that was wrong, someone else sort of had that thought too. You weren't the only one. So yeah, this is basically just like an R squared for the model, right? And this is fine and it's nice and it's interpretable, but we know that our eta squared value is sensitive to the number of the effects in the design. Okay. If I go through and I have something that's multiple factors, my sum of squares effect is going to be only the sum of squares that's unique to factor A, and then factor B and sort of interactions and stuff like that get pulled out, which starts to make that sum of squares effect start to be systematically smaller, right? And for our repeated measures designs, our eta squared includes all the stuff in the denominator as error or as total, even though it's stuff that we've accounted for, right? So even if it's variability that we've accounted for, it still gets dropped into that sum of squares total there in the bottom. And so the concern is as a result, our eta squared might underestimate the magnitude of our effect. Now we know that eta squared is systematically positively biased, just as it's, but positively biased in that the actual population effect is probably smaller than what we get, right? But in general, eta squared or even omega squared statistics, we're concerned with the repeated measures that it's going to underestimate magnitude of effect and not permit sort of reasonable comparison across studies. Okay, so we've got our partial eta squared. This is giving us an index or effect in the context of unexplained variability. Okay, here we're going to go take our sum of squares effect over our effect plus our error, right? And our error is just what's not been accounted for by other things. Our partial eta squared is going to ignore everything but the effect of interest and the unexplained variance, right? Everything else that's explained gets partialed out. Now, this is what we're talking about in terms of our partial and our semi-partial, or our partial correlation, not our semi-partial correlation, but our partial correlation, okay? What we're doing is we're capitalizing on other variables and controls, preventing underestimation, makes this a better effect size estimate to sort of go through and compare across studies, okay? But when we go through and we're talking about repeated measures designs, the problem with partial eta squared is that we've got multiple sources of error, okay? What we did, and think about what we did in that example with our depression clients, all of the between subject stuff that we didn't account for, right? All the individual differences got sucked out of that, right? That's still variability, right? That's still stuff that we haven't accounted for, but on our repeated measures designs, our partial eta squared isn't gonna count that, right? It's gonna get all pulled out. And so the concern is that on our repeated measures design, when we have error that's associated to just individual differences, plus error going on with our repeated measure stuff, in the calculation of eta squared or partial eta squared, it's just this stuff that's going in. We just ignored and pretended all that wasn't there. And so the argument is, and the concern is for repeated measures design, is you're going to get massive partial eta squareds when maybe that doesn't actually reflect the extent to which these data are accounting for, or the effects are accounting for stuff in your data. Okay. So one of the things that's been proposed in order to make our effect sizes comparable across between subjects designs and repeated subjects designs is going to be the calculation of generalized eta squared. Okay, generalized eta squared is going to be looking at your effects within the context of all sources of unexplained variance in the calculation of your effect size. Okay, we can calculate this from SPSS, but the specific formula for generalized eta squared is going to depend on your study design and your specific effective interests. Okay. And the thing is because SPSS doesn't know what your design is or the specific effective interest, it doesn't calculate this for you, right? You can go through and do it so long as you know where there's variance components are falling out and what to go through and do and how to grab your specific stuff, okay? Now for generalized eta squared for a one-way repeat measures ANOVA, our generalized eta squared for this design is just going to be our sum of squares repeated measure over sum of squares repeated measure plus sum of squares between plus sum of squares error. Okay, so what you can see what we're doing here with our generalized eta squared, here we've just got our effect over our effect plus our error. Generalized eta squared for our repeated measures design, we're taking all this stuff that we had ignored with partial eta squared and we're putting it back in the mix, right? Which is going to make my effect size much smaller, but it's going to make it more comparable to the types of effects that I would see in, like, say, a between subjects design. Okay. So again, in most cases, our partial eta squared is going to be the largest, and our generalized is going to be here, and our eta squared is going to be here, just in terms of thinking about what's going in and what's included in that denominator. Okay. So in terms of thinking about generalized eta squared is nice because it can sort of take into account the nature of your design, things along those lines. And so arguments would be, we should be generally preferring to be reporting generalized eta squared across the board. You've got a Bakeman article that's assigned for conceptual computational details that you'll spend some time with finding out how to go through and pull this out for different types of designs and things along those lines. What I will say is if you take the methodological high ground, if you got people who are in the know, who are like into this stuff, like this is something that will make them excited to say like, oh boy, this person knows what they're about. You know, they've gone through and reported generalized eta squared. The downside is generalized eta squared. It's a tough pill to swallow when you look at your partial eta squared that you get in your SPSS output and then you calculate generalized eta squared. It's going to be much smaller, right? And I'm not going to say that you can't get away with publishing things where you're not calculating generalized eta squared. What decisions you make is sort of your decision to make. What I want you to do is just know kind of where these metrics are coming from, what the difference is, and how they relate to one. Okay. So in terms of calculating generalized eta squared for my inpatient depression sample, here we've got our sum of squares effect over our sum of squares effect, our sum of squares between, and our sum of squares within error. It's going to give me a generalized eta squared of 2.63. Okay, so you can go through, take a look at this, take a look at your output. You'll be able to see where these numbers are coming from to go through and pull this apart, right? So we could say generalized eta squared for the main effective session indicated that repeated assessments counts for about a quarter of within subject and between subjects variability in BDI scores over the course of intervention, right? I'm just talking about this to sort of talk about what variability we're capturing. Yeah, Kate.
Sum of squares effect, you said, is repeated measure?
Yeah. Same thing here for our post-trauma support. We got a much smaller effect here, right? Here, we're saying that event type is calculated for about 3.8% reduction. A 3.8% reduction across within and between subjects error for ratings of willingness to provide support. I've just gone through and just talked about this differently, right? Here, I'm talking about this in terms of portion of variability and within and between that's accounted for, right? Here, what I'm doing is I'm sort of framing it in terms of a reduction in error, right? Here, I'm saying that like we get a 3.8% reduction in error, and we account for this, right? So again, it's the same thing. I'm just talking about it, different ways to think about this and conceptualize it.
Yourself with that one.
I did, yeah. Sometimes it is, you just like throw stuff in there, just like sort of make yourself laugh, right?
Is that your cat?
That's my cat.
Thing
That's-
that always does.
That's someone's homework.
That looks just like if you were a cat, that's right.
No, you just called me the handsomest boy. Yeah, he's likes to help out. So,
He's very helpful.
yeah,
His
his name is Lionel.
Call Mr. Snuggle.
Yeah, right? Okay. So. Clear on calculating effect sizes, calculating sort of our sort of main effects of our repeated assessment, right? Any questions on any of that piece of things? Okay. What we need to do now, though, is start to determine where our specific effects are at, okay? Again, we need to go through follow-up on this. As with any omnibus test, our omnibus test just says that there's something in there, right? What we needed to go down through now is figure out where these effects are hiding out. What makes it start to become complicated with our repeated measures designs is that we've got additional model assumptions as we've gone through and added multiple assessments, and we have both the possibility of within and between subjects effects. We have to account for, at this point, we don't have any betweens, but we definitely have withins. And when we start to factor in grouping variables in this, now we've got a lot of different places where things could drive the effects that we're seeing. So common approaches are going to be trend analyses that we'll talk about, contrasts and plan comparisons, and post hoc testing. Now, the only thing that we haven't talked about previously is trends. These two things are exactly the same as all the stuff that we did last semester. We're just taking it into consideration that we're accounting for both between and within stuff, okay? And so again, the strategy for evaluating these effects are going to be determined by your hypothesis. Hopefully you have some idea of what you did to start out with, right? For the repression example, right? Like hopefully we're like, yeah, we're expecting these scores to decrease across the course of intervention. That's pretty specific. Maybe you have some more unique hypotheses about how things should see the greatest change within the first 2 weeks with less stuff going on afterwards, something along those lines. But I really can't emphasize enough, having an idea about what you're expecting to see before you jump into this is going to be hugely helpful. What you don't want to do is end up looking at all possible combinations of all possible things, because it'll be a nightmare and you'll never get a story out of it, okay? There's some conceptual considerations that you want to be thinking about, right? Like, do I have ordered effects? Do I have not ordered effects? How do I go through and think about this? Aspects of the design that'll start to come into play, and the number of types of effects that you go through and observe. So lots of different things. Like, you for sure want to have a game plan. Don't just jump in and start like trying to run t-tests and stuff like that, because you're getting quicksand, you drown right away, because there's just too much stuff to be going on, right? So very, very clearly want to have a good conceptual idea of what's the analysis, what am I doing, what am I hypothesizing, why am I doing this in the first place, and then putting together a game plan on how I want to go through and tackle these effects. So, quick review, right? When we've got multiple comparisons, lots of different things we can go through and test. Want to be thinking about different types of error. Our per comparison error rate, this is going to be the probability of committing a type 1 error on any given test. This is set by alpha, right? I say I'm gonna set my alpha to equal 0.05. I'm saying for any given test, I'm saying I want the probability of a type 1 error to be no larger than 5%. We have family-wise error. This is the probability of committing at least one type 1 error across the series of comparisons. That's saying I'm gonna make 4 comparisons. What I wanna do is wanna set the probability of making at least one type 1 error across the whole set equal to something that I'm sort of comfortable with, okay? Family-wise error is gonna be given, remember, as 1 minus the difference between 1 minus alpha taken to the C power, where C is gonna be equal to the number of comparisons that you've got. Okay, so again, your family-wise error for 4 comparisons, each at 0.05, gives you a family-wise error rate of 0.185. That says the probability of it making at least one type 1 error in that series of 4 comparisons is getting close to 20%. That's not a lot, but probably a lot more than we're comfortable with in terms of the context of science, right? I wouldn't even probably sit down at a casino game for that, because you're gonna get taken for a ride, right? So just thinking about that in terms of so what we're thinking in terms of these probabilities. Our family-wise error is gonna be bounded by alpha and C times alpha, right? C times alpha, this is related to your Bonferroni correction, right? Generally assuming that your family-wise error rate is gonna be close to that number of comparisons times your alpha rate, right? So just in terms of trying to manage, kind of thinking about like, what's the likelihood or the probability of making type 1 errors across this set of tests, okay? So recommendations, again, particularly for these types of repeated assessments, only look at comparisons that are meaningful. Like if there's a comparison in there that you couldn't stand by and defend and say, this is why I've done it, and this is why it's important, it probably means that you don't need to look at it. Doesn't mean someone won't ask you for it, but this is why providing all your descriptive statistics is nice. Be like, I don't know, it's free country, look at whatever you want. It's all there, you can take a look at it. These are the things that are important to me, right? Again, testing all possible comparisons is not interesting. It's generally not meaningful, and it's going to be a giant headache for you. Because then if you go through and test it, I expect you to talk about it, whether you found evidence for it or not, because I'm assuming if you did it, it was important. So you tell me why, and then tell me how this informs theory. If you can't do that, it's probably not a comparison that you should be making, okay? From a statistical standpoint, wastes power, it complicates things. You got to say too much, and you're just kind of making stuff up at some point, okay? So what you want to do is choose a strategy that manages your family-wise error across your planned and unplanned comparisons. SPSS won't do this for you. SPSS will just belch out a bunch of stuff, right? And then you're free to comb through it and cherry pick the stuff that you like. But essentially what you've done is you ran 150 different comparisons and just pulled out the 3 that were significant and then talked about those. But from a science standpoint, what you've done is actually you ran 150 comparisons. And the fact that you found 2 is actually disheartening to me, because I don't know what that means. It probably means those are type 2 errors or type 1 errors, right? So wanting to think about how do we go through and manage this stuff, okay? Best advice coming out of Howell, right? Just have a good reason for looking at the comparisons that you're making. Like in science, with everything you do, be able to just stand next to what you did and be like, this is why I did it. I thought about this, thought about this. These were the considerations I had. Never just do something to do it, or because you think you should do it, because then you're going to have to eventually, at least in terms of theses, papers, things like that, you're going to have to defend it. And it's going to be really hard if you don't understand why you did it or think it's stupid to begin with. Unless reviewers are making you do it, that happens all the time, and then you got to sort of deal with that. Okay, so follow-up tests. Think about a priori versus post-hoc stuff. Okay, our a priori comparisons, this is typically going to be our small set of comparisons that are theoretically meaningful that we planned before we even collected the data. We're saying, this is my conceptualization, this is my question, these are the analyses that I'm going to do. I know what the results of that analysis are going to look like. These are the specific things that I want to go through and compare and test, okay? Looking at this generally through contrasts, independent sample t-tests, and traditionally, by convention, if I've called my shot before I even went through and collected my data, I can look at those at per comparison error rates, right? Now, if I have 15 a priori comparisons, then that's maybe getting ridiculous, right? Again, key here is small set of theoretically meaningful comparisons. But if I want to be conservative, I can go through and start correcting for family-wise error, even within those planned comparisons with a Bonferroni or a density. If I just want to be, if I'm not concerned about the possibility of making a type 2 error, okay? The only thing that I will say, make this decision before you run it, not after you run it. What happens is people will go through and say like, oh, all the things I want to talk about are P less than 0.0001. And the stuff that's less convenient to talk about is 0.02 or something like that. So now after I've seen my results, then I'm going to go start through and applying a Bonferroni correction. Don't do that. That's for sure cheating. Okay. And misses the point of running these things. Also, remember that Bonferroni, Dunsitick, these are not post hoc tests. These are very stringent corrections that are intended for planned comparisons. If you go through and Bonferroni correct for all possible pairwise comparisons, it's going to make your threshold for identifying effects way too high. And the only thing you're going to pull out is probably stuff that's wildly overestimated anyway. And it's just going to perpetuate to this publication of inflated effects and things like that we already have concerns with, right? So want to think about, it seems like the right thing to do would be take the most stringent approach. From an actual method standpoint, that's actually kind of irresponsible because what we're probably doing is only grabbing the stuff that's ridiculously inflated that no one will ever replicate an effect size of that just because it's a weird finding in my data, right? So being careful in terms of your selection. Okay. Post hoc comparisons, on the other hand, these typically involves looking at all possible pairwise comparisons. Idea is that, boy, after I've got my data, after I've looked at it, then I'm like, oh, these are the things that I want to take a look at. Well, fine, right? But what you've actually done is you, in your mind, ran all possible comparisons and just picked out the ones that are most interesting, probably going to be the ones with the biggest difference. And so what we need to do with your post hoc comparisons is control for the fact that in your head, like in the blink of an eye, you went through and ran 15 different pairwise comparisons and decided that these two were the ones that where you were really interested in looking at. Well, you're not just making one comparison, you went through your head and did all of it, right? So we have to go through and correct for those, okay? Get these really easy in SPSS, but the problem is if you aren't interested in all possible comparisons and you already had some ideas about what's going on, you're gonna get taxed for all the stuff that you don't care about anyway, and that's gonna become problematic, okay? So again, limited set of planned a priori comparisons that have some theoretical methodological basis. This is always going to be your best bet, okay? In other areas of science, right, Johnny, if we're in econ or marketing or something like that, and we're just like throwing everything in there, and for just this one situation, I want to maximize my output, then go through and sort of stepwise regression, pull things in, pull things out. If I don't care why it's predicting anything, who cares? Then fine, whatever. But this is rarely the type of science that we're doing, right? And so always wanting to have a strong rationale for what you're looking at and why. And if you do decide to look at all possible comparisons, you should have a really compelling reason for why there was no possible way you could make any predictions on the front end and needed to just go through and slog through all possible comparisons with stuff. Okay. So even remember, and I kind of do this on purpose, last semester where you had to do post hoc stuff on that factorial design and you had like 15 different comparisons to go through and run and talk about. Was that fun? No. It sucks to try and think about like, how do I tie all this together in some sort of cohesive message? It seems like a good idea, but once you get in the middle of it, you're like, ah, nuts. Now how do I go through and talk about all this? Because I got weird random effects that come up that I'm not interested in, that I don't think mean anything, but I have to go through and now defend why I went through and looked at it. Because I can't just be like, oh no, I like this effect at 0.032, but this other one at 0.035 that's probably a mess. Don't ignore that one, right? Can't do that. So we kind of straitjacket ourselves with all possible comparisons. Okay. Questions about post hoc plan contrast things along those lines. Okay. So if I have a repeated measures design that has some ordered mean, right? typically what I'm most interested in is the pattern of effects across repeated assessments, okay? When I'm going through and taking a look, let's think about that depression example that we went through and took a look at. Probably what I'm most interested in here is that trend, Mesa, in terms of you're like, yeah, it looks like people's scores are going down as treatment continues, right? Whether or not people's scores are different at 2 weeks versus 3 weeks is probably not a very specific interest. Like there might be, maybe there was something at 2 weeks to 4 week assessment that was like a critical sort of treatment, something that happened, but probably you're just looking at over the course of treatment, sort of where things going. In this case, trend analyses is going to go through and provide a test of the shape of means across your repeated assessments, okay? Your differences are going to depend on both the magnitude and the order of your means, right? So for that example with the BDI scores, a trend analysis might be a nice way to go through and follow up on that. I'm expecting scores to just decrease over the course of intervention. And what I can do in when we went through and we said that trend analysis thing, they're like, okay, skip that, we're going to go back to it. That's essentially what was going to go on with that, right? Most of our trends are going to be put linear or quadratic. We can have other polynomial effects, but those are going to be less common. Like if I have a third order polynomial, right, where I'm expecting 2 bends, that's a pretty specific pattern of behavior that I would need to account for, right? The number of assessments that you have also determines the number of repeated, or the number of or the polynomial that it'll give you, okay? SPSS, if you have those polynomial trends, it'll just go through and spit out as many as you have. Like, so we had 4 assessment points. So that will give you a linear, a quadratic, and a cubic, I think. Okay. And it's just going to dump them all out there, right? Now, the nice thing is if I just have an assumption that, hey, I'm going to see some linear reduction in these means over the course of treatment, I can go through and take a look at that. And essentially what it is just a planned contrast. It's just going to go through, run the same way as a planned contrast with sort of using specific weights to capture linear, a pattern of linear differences across things. You can go through and do these by hand if you want to. Like you would set it up the same way you would set up any contrast. It's just easier to let SPSS do it. The only downside is what's going to happen is if you look at that indiscriminately, likely what you're going to have if you have a number of repeated assessments, you might go down through and find that your 4th order polynomial, right, is significant because it has a low p-value. That probably doesn't mean anything unless you have some reason to expect the scores are going to increase, decrease, increase, and then go back down. That's starting to get some pretty nuanced stuff, right? It's going to go through and it's going to run and it's going to test things. It doesn't mean that it's going to mean anything from a theoretical or conceptual standpoint. Okay. Now for our depression scores, linear is obviously going to make some sense, right? And if I saw that I had a linear effect in that, that could be useful because it's just saying, yeah, we have evidence that that these data do conform to a linear trend, right? So they're suggesting that across repeated assessments, scores are decreasing. With that, you could also even make an argument maybe for a cubic, right? Because we see, and oftentimes we see as people get better, like you don't get better at the same rate indefinitely. Eventually you kind of taper off, right? Which suggests kind of a bend going on there. So we might be able to interpret that cubic trend to say that, yeah, it looks like these patterns of means are decreasing, but the deceleration is increasing as we move forward. It starts to flatten out, right? Problem is though, if you go through and start back, oh, and my 5th order polynomial was significant in these data, like cool story. But I don't know, what does that mean? Would you expect that? Does that mean anything? Or is that just something that popped up on your output with a really small p-value that you got excited about, right? So have to think carefully about this. But in cases where we have ordered means, this can be one way to go through and approach it, okay? And so you're not looking at, is this point different than this point, or is this point different than this point? You're just looking at, is there a trend that's linear in nature? Questions about that? Okay. However, when we go through and we look at unordered means. Now trend analyses aren't useful, right? Because there's no real order to these, to my vignettes. I can put those in any order. And if I swap around the order, it's going to completely change the pattern. My omnibus spec doesn't care. Like I can put those in any order I want. For the overall, it's just looking at their differences. But as I start to follow up, trend analysis isn't super helpful. Okay. My repeated measure doesn't have any meaningful order, right? Or my repeated measure does have a meaningful order, but my responses don't follow some sort of polynomial function, right? So it's not sort of one of these sine wave types of things with different bends in it, right? I've got some pattern that does make sense to me, but it just doesn't follow sort of one of these polynomial trend analyses very well. In this situation, we're going to follow up just with plain contrast and paired sample t-test, just like we did before. Okay. Quick run through of our contrasts. Remember that our contrasts are going to allow us to go. Contrast is any comparison that you run is a contrast, but our linear contrast is going to allow us to run comparisons between pairs of means or sets of means that I think might be theoretically interesting. Okay. This is a flexible approach. And again, remember that this is just a generalization of the t-test. You're just doing a t-test with this. You just have to assign the proper weights to things. Okay. So again, remember here, I've got a linear contrast is just a set of weighted means, right? And I can put this down as my contrast is equal to weight of x1 plus weight of x2, weight of x3, so on and so forth. We can shorten this to just call this the sum of the weighted means, right? Our equation here is simply identifying just a combination of weighted means. If I set all these equal to 1, then my contrast is just the sum of the means, right? If I set these weights as 1 divided by k, my contrast is just going to be the mean of all group means, right? So we're just playing around with these weights in order to get something that makes some sense. Okay. Now recall that when we have a contrast where the sum of the weights are equal to 0, this is our linear contrast. Okay. Again, if we have 3 means here and I assign weights of 1, -1, and 0, I have a linear contrast here. Okay. I go through and I assign those weights. And essentially what I'm doing is I'm just looking at the difference between group 1 and 2, right? I'm looking at group 1, group 2, group 3, I assign a weight to 0, it takes a hike, and all I'm doing is looking at the difference between these. And if this is the way I've set up my weights, Daniela, who am I hypothesizing is going to score higher than who?
The A1.
Yeah. I'm saying 1 is going to score higher than 2. If I switch that around, does that ruin my contrast?
Doesn't ruin it, but does it?
Doesn't ruin it. I'm still going to get the same p-value. It's just my sign is going to be in the opposite direction. I'm going to have to sort of make sure that I know what's going on, right? If I go through and I assign that negative to the group that I think is going to be lower, then whatever the sum is, it just sort of makes some sense in terms of the group that is higher than the group that I expect to be higher is actually higher. Okay. So again, let's switch this around, set 1/2, 1/2, -1. Again, sum of my weights is equal to 0. What I'm doing here is just looking at the combination of group 1 and 2 versus group 3. Okay. And again, this is really nice. If I've got a set of groups, I could look at group 1 and group 3 and group 2 and group 3 and group 1 and group 2 together. That's a lot of work, right? If I've got an experiment where I've got control experimental group, right? Well, these 2 controls should be about the same. So I'm just going to group them together, see if they look different than the other one, right? I just saved myself a bunch of time and have presented this in a much more parsimonious way than a bunch of pairwise comparisons. So again, when we're going through and selecting coefficients, again, this is all review. First, one is identify the set of treatments to be compared. Which groups do I want to be included in this comparison? Then I'm going to assign weights as the reciprocal of the number of treatments in the set. And so if I've got 3, then I just assign my weights to 1/3. If I've got 2, it's 1/2, so on and so forth. And then I just assign coefficients of one group to be negative. Typically, it's going to be the group that I expect to score low, right? So 5 means I want to contrast 1 and 2 versus 3, 4, and 5. Go through, here are my means. set up my weights as the reciprocal of the number of groups in that set. So here we've got 1/2, 1/2, 1/3, 1/3, 1/3. I think this set of means is gonna score lower. I assume I assign negatives to that. I add 1/2, 1/2, 1/3, 1/3, 1/3, sum those up. I get the sum of 0 of my weights, just means I have linear contrast, right? Go through, set that up. And it's giving me a comparison of these two versus the combination of those three. With my linear contrast, if I take the absolute values of those sum to a value of 2, this is giving me a standard set, okay? Remember that this is gonna be relevant in calculating my effect sizes. There are an infinite number of weights that I can assign to this to get the same comparison, to get the same p-value. But if I go through here, if I add 1/2, 1/2, 1/3, 1/3, 1/3, I get a value of 2. That means the value of my contrast is gonna be sort of represented in actual units that I actually measured. And that's nice because then I can just use that value of my contrast when I'm calculating effect sizes. Note and remember that if I have dramatically different sample sizes across cells, this complements the calculation of my contrast. It screws stuff up. Again, we don't need to worry about this with a one-way repeated measures ANOVA. When we start factoring grouping factors into things, this will become relevant. So linear contrast for my repeated measures ANOVA, okay? Contrast for my repeated measures ANOVA is now we've got kind of a paired sample thing that we need to go through and account for. My contrast is just gonna be the sum of my weighted means, okay? My t-test though is gonna be the value of my contrast over the sum of my squared weights times mean squared error from my repeated measures table over the number of people in my sample. Mean squared error taken from my overall ANOVA table. Test statistic is evaluated against a critical T with degrees of freedom of error taken from my ANOVA table. So this is just all the same stuff that we did last semester. Okay. For pairwise comparisons, also defensible to fall back on paired sample t-tests. Okay. Primary concern with this is limiting the number of pairwise comparisons that I have, right? If I can sort of group these together with a contrast, that's nice. But if I start to violate assumptions and things like that, things are looking funky, a paired sample t-test is a perfectly fine thing to do. It's going to be a less powerful test, okay? But it's certainly something that is reasonable. Okay. So thinking about some considerations, right? In terms of with these contrasts and where things are pulling from. With these contrasts, I'm always pulling my error term from my overall ANOVA table, right? And this is fine so long as I don't have violations of homogeneity, sphericity, discrepancies in the effect size or in sample sizes. There's just with these repeated measures designs, particularly in my factor or my repeated measures ANOVA stuff, there's just a lot more stuff to go through and account for, right? The procedures for my contrasts are created assuming that we have no violations of our assumptions. We're pulling our error term from the overall ANOVA model, right? The problem is if we start, and if we do this and we run a tight study and everything's looking good, we have great benefit in terms of power to detect specific effects. Problem is that's not how real research works a lot of the times. And what can happen is if I have a lot of stuff going on and a lot of warts in my data, what I start to be worried about is, boy, can I trust those tests because I pulled an error term from an analysis that violates a whole bunch of assumptions. And so that error term is maybe not 100% reasonable for the types of things we're doing. In this case, falling back on t-tests is perfectly fine, right? You just say, you know what, there's a lot of stuff going on here. I don't feel comfortable running a bunch of elaborate contrasts that are assuming that there's nothing wrong in my data when I know for sure that there is. And so what I'm going to do is I'm just going to follow back on some t-tests to go through and try and tease out where my stuff's going. All right. All possible comparisons. We can do this in SPSS. We can just go through and my repeated measures window. I can hit compare main effects, select LSD, Bonferroni, Duncitic. You can do this. This is something that it will give you. Don't do this, okay? It's not going to correct, at least, Fisher's LSD, is just paired sample t-test using degrees of freedom from your overall model. So it's just like a hyper powerful t-test, paired sample t with no correction for anything. Bonferroni and Duncitic, these aren't post hoc tests, so it's going to assign too big of a penalty. And what it's going to do is it's going to alleviate you from actually thinking carefully about stuff. What you're going to do is you're going to find weird p-values or weird comparisons that have really high p-values. It's going to be a distraction from what you're actually trying to do. And it's going to tie you into trying to explain something that very well could be not something that's generalizable or interesting, but just a weird thing that's going on in your data that no one will ever see again in the universe, okay? So just want to be aware of this stuff, okay? For your post hoc tests, you can go through and you can run Tukey's. Remember, we can bend Tukey to our will, right? We can go through and calculate a Q critical from our table values, then just run a bunch of t-tests at those based on that Tukey critical, compare against the Tukey critical and just see like, hey, are these things turning up, and go through and say, okay, using this to say this is an approximate correction for whatever my alpha is. We also have our Benjamini-Hochberg. Remember, Benjamini-Hochberg, a little bit different. Our corrections for our family-wise error rate is concerned with the possibility of making at least one type 1 error in a whole set, right? Benjamini-Hochberg is looking at false discovery rate. And what we're asking here is what percentage of my significant effects are false positives, right? So it's less than like, hey, if I make one type 1 error, the whole set is spoiled. It's saying, what's the likelihood of me making a mistake on each individual test, right? And so again, here, you remember we did this last semester. What you do is you determine a critical p-value for successive contrasts, right? This is calculated as 1 over your index over your number of comparisons times alpha, right? And we just remember we went through and did this. You just go through and you run your comparisons, right? And then you have kind of this adaptive progressive criterion, right? So for your lowest or for your highest, your test with your highest p-value, or excuse me, your lowest t-test, right? Your least large difference, essentially. That goes first all the way up to your largest one. And then you just have a descending criterion here. So it starts at 0.05, 0.02, 0.03, 0.25, so on and so forth. Now here for our depression scores, is comparing differences across individual time points really necessary or meaningful here? No, because you just got, like, I don't need a statistical test to tell me they're different. They're very much different, right? But here we've got 3 versus 4, 2 versus 3, 2 versus 4, 1 versus 2, 1 versus 3, 1 versus 4. As we step it all down, they're all very clearly there, right? So this is an example of an application where we could do something like this, but it's kind of boring. It doesn't tell me anything really useful or interesting. I knew what was going to happen to start with, and so it's probably not a good strategy for that type of analysis. Awesome. All right. We are making fantastic progress. Next class, we will probably be, if we don't get this knocked out of the park, we'll be very, very, very close. Okay. So again, with this last assignment, we'll go through and talk about like when we could think about this. We could move back. So this last repeated measures assignment is due last day of classes, and we could certainly sort of keep that there. But if you wanted to go through, and maybe you'll just let individual people sort of do what you want, but if you wanted to, once you get your logistics knocked out, if you wanted to jump on this and get this set up before the very last day, that would be a real brilliant move if you wanted to do that, just so not everything else is slammed there at the end. Now I know but you're free to make your own decisions and stuff, but I would very much think about that in terms of jumping on this early, so it's not sort of feeling all the pressure, sort of, and then you turn in an assignment on Friday. Matt and I got to scramble to get those turned around and back to you. so that you can look at and go into this final assessment on finals week. So just thinking about this in terms of, you've got lots of leeway, we still got lots of time, but want to give yourself enough room so that you don't feel like you're grounded there at the end when everything's miserable. So,
I
yeah,
have a question. If we're gonna potentially finish up next week with this, what do we do moving forward from that?
yeah, so we've still got, and people, if you did sort of take off, sort of go through, take off, you don't have to sit here. Field questions, we've still got that ANOVA set.
Oh, yes.
Right, so that we'll go through, that won't be included on this stuff, and I don't have assignment attached to that. But we'll go through, that's sort of a common analysis that's interesting to go through and take a look at, we'll look through that. And then, I don't know, I mean, you know, I've got, what's that?
Sorry.
Well, I know, I thought about that. It's really use this like a catch-up session to just go through and kind of go through and talk about things. I also have like slides for exploratory factor analyses that we've not gone through and done, like some people like, oh, hey, I want to learn about this. Some people not, so I don't know, like there's things that we can go through and kind of play around with that if we get finished up early. So sounds good? Awesome. All right, everybody, thank you.
The dog birthday. Hi, hello. Cause he thinks I'm a dog.